Rotating machinery exhibits specific characteristics when faults create unwanted mechanical motion. These faults often create forces that cause the machine's shaft center line to be periodically displaced from the machine geometric center. For over 70 years, machinery vibration analysis, or MVA, has been the main method used to identify many of these faults. Recent experience and research have proven that many of these same faults can be identified using electrical signature analysis, or ESA. ESA also provides very important information regarding the condition of the incoming power to the motor, as well as possible electrical faults in the motor system undetectable using MVA. This presentation discusses the faults that are identified and how they present themselves in both the vibration spectrum and the electrical spectrum. ESA is emerging as a very important part of a plant's electrical predictive maintenance program. In some plants, it is being used as the main detection tool used to identify both electrical and mechanical problems on machines that are driven by electric motors. Companies that have a large population of rotating equipment have made a large investment to provide a product or service. Maintenance is required to protect this investment and keep the equipment operating at their maximum capabilities. Additional pressures are created by the continued economic conditions that require companies to reduce costs while maintaining, or in some cases to even increase, these products or services. An effective method of meeting these pressures is by reducing the cost to maintain this equipment by implementing an effective predictive maintenance program. It has long been recognized that predictive maintenance can reduce the cost of maintenance. More importantly, it is being recognized that greater savings can be achieved by not only identifying faulty machines using predictive maintenance, but to use these same techniques to identify what is causing the failures and then taking actions to prevent these failures from occurring. Predictive maintenance programs are based on studies, like the Nolan and Heap study, that have determined that 89% of failures are random in nature and that 68% of failures occur immediately after installation or repair. Generally speaking, this means that the probability of a failure actually increases by performing routine preventive maintenance tasks and inspections. Predictive maintenance programs use the machine's operating condition to determine when maintenance needs to be performed. The most effective programs recognize the three phases of predictive maintenance: detection, analysis, and correction. The detection phase is the most important phase. In this phase, the goal is to simply identify machines with developing faults. These faults should be identified with enough time remaining to remove the machine from service before a complete failure occurs. To maximize the effectiveness of the program, it is important to survey as many machines as rapidly as possible. The faster these surveys can be performed, the more machines can be monitored. Once a faulty machine is identified, the analysis phase is used to more thoroughly identify the problem. This phase may require additional testing or even another technology to determine the severity and cause of the failure. The correction phase requires replacing or repairing the failure and verifying the correction. This is also the ideal time to correct the reason for the failure. Predictive maintenance instruments should be portable, lightweight, easy to use, and perform repeatable, non-destructive testing. There are many varying technologies and instruments that can perform this very important process. There is no single measurement or technology that provides insight into identifying 100% of developing machinery faults. Machinery vibration analysis has been an integral part in most successful plant reliability programs. It has proven to be a very important tool in identifying developing failures on rotating equipment for over 70 years. During that time, tremendous strides have been made in implementing these programs and understanding, identifying, and determining the severity of the mechanical faults this technology can identify. Machinery vibration analysis relies on the mechanical forces created inside the rotating machine to cause the casing of the machine to respond to the applied force. According to Newton's second law of motion, force equals mass times acceleration. The mechanical motion created by the internal forces is measured by a transducer, which converts this mechanical motion to an electrical signal. The vibration instrument performs a fast Fourier transform on the transducer signal to determine the frequencies of measured forces. Therefore, with MVA, the ability to identify developing faults is limited by the machine's design, mass, and structure. Many developing faults may be buried in the background of the machine's normal operation, or the developing fault forces may be insufficient to move the bearing support or other parts of the machine that are being measured. The earlier the fault is detected, the more effective the program becomes. Electrical signature analysis measures changes in the motor voltage and current to identify faults in the electric motor system. ESA determines the condition of the power coming into the plant, as well as electrical faults in the electrical distribution and control system, as well as in the motor itself. Because ESA measures changes in the motor current to identify developing faults, it is not limited to electrical faults, but can also identify developing mechanical faults within the motor, the driven machine, or the process itself. Even very small changes in the machine's condition can be detected anywhere in the motor system. The electrical motor system consists of the electrical and mechanical subsystems. The mechanical subsystem consists of the motor shaft, coupling, driven machine, and the process itself. Since all of these components are mechanical in nature, they are subject to any fault associated with rotating machine. Faults such as unbalance, misalignment, bent shaft, cracked shaft, mechanical looseness, oil whirl, rolling element bearing faults, vane passing forces, gear meshing, flow, and other hydraulic faults are identified using MVA if the force is strong enough. These hydraulic or mechanical faults create forces which are applied from the shaft to the bearing and bearing support. These forces cause the bearing housing to periodically move at the frequency of the applied force. The amount of the motion depends upon the strength of the applied force as well as the mass and stiffness of the structure. Because of this limitation, early indications of many faults remain undetected, and several measurements are required at different locations on the motor system, usually at the bearings, to identify developing faults using vibration analysis. The electrical subsystem consists of the incoming power, the internal distribution system, the motor starter, controller, and the motor winding and rotor system. The types of faults that occur in the electrical subsystem are mostly electrical in nature. Incoming faults range from voltage mismatch, unbalance, or non-sinusoidal input. These faults can come directly from the supplier or faults in the internal transmission or distribution system. Non-sinusoidal input can cause negative sequencing that creates internal heating. Insulation life reduces by approximately 50% for every 10 degrees C the temperature exceeds its upper limit. Heating of the windings insulation creates winding shorts and grounds. Additional faults in the electrical subsystem can be caused by improper assembly of the rotor-stator system, in other words, unequal air gaps, loose or broken rotor bars, or eccentric rotor. Since each of these faults affect the motor current, electrical signature analysis identifies these faults even in the very early stages. In addition, since ESA performed power quality analysis, it evaluates the condition of the power supplied to the motor system, and this will identify any problems from the incoming power or the internal distribution or motor controller. Any of the mechanical faults from the motor or the driven machine or the process itself will also affect the current draw on the motor, allowing it to be a very good and sensitive sensor to detect most electrical and mechanical faults throughout the motor system. This is accomplished from a single measurement taken from the motor controller. While MVA has been around for over 70 years, ESA is relatively new to the predictive maintenance market, but it is proving to be one of the most useful technologies for performing the all-important detection portion of the predictive maintenance program. Not only will it identify all of the mechanical faults that MVA does, but it also performs a power quality survey to determine the condition of the power feeding the motor system. Research and testing has shown that ESA is also a very good tool for identifying developing faults in variable frequency drives and DC controllers. In many cases, ESA has identified rolling element bearing failures earlier than traditional vibration measurements. Other areas of testing have also shown that since ESA uses the motor current as the transducer, ESA can identify problems in machines that have proven difficult, if not impossible, using MVA. One very promising area has been identifying pump problems in vertical pumps. It has been well documented that MVA cannot identify problems in the pump or other parts of the pump that are below the surface by making measurements at the only accessible locations on the motor or the discharge stand. A recent test on a 750 horsepower condensate vertical pump in a cogeneration plant clearly showed destructive vane passing issues using ESA. Vibration readings taken on the top of the pump showed the pump to be in excellent condition. Subsequent inspection of the pump showed severe pump impeller damage. Other areas of testing are overhung fans and wind turbines. This presentation is based on a white paper recently given by William Kruger, Technical Training Manager, Altest Pro, at the Vibration Institute 2010 National Technical Training Symposium in Oak Brook, Illinois. The paper is titled Electrical Signature Analysis: How does it compare to machinery vibration analysis, and where does it fit in your plant's reliability program? For an electronic copy of this paper, please email info@altestpro.com or call us at 860-399-4222. Thank you for listening to this presentation, and we hope you found the information interesting and helpful. For more information about improving motor system reliability, go to altestpro.com.